All right, let's get started. Sorry about the late post for class. I was just finishing up dinner and, finished that up, ran up here. So let me go ahead and screen share to get us started. We're picking up where we left off yesterday, essentially. And to that end, I know some of you definitely tuned in to the study hall today, and we kind of covered some of what we're covering today in that study hall, but sort of passed over some of it and covered the PMF in general. We are on the edge of wrapping up the sampling approaches, and so we'll want to review this code just a little bit. I think that'll be helpful as we keep going with this. So let me just track down where we were. We had just done the sampling process, one trial of 1,000 samples. We compared that to one trial of 100 samples, and we saw some output between those two. And I think I just want to kind of reaffirm this output, and maybe instead of 16, I'll change this to 8 bits. And in all likelihood, I'll need to reshare this code. But before I do that, let me just show you this output. So this is 8. This is a binomial distribution with a number of trials being 8, and number of samples either 100 or 1,000. So, whoops, let me save that. And we'll say Python, this is binomial. And I should probably put a space in between these two, just so that it's a little cleaner. Okay, so let's look at this. In this 100 trial version, we're still seeing it being much more likely that we get 4. And this isn't doing that poorly, just honestly, it's not that bad. We get a little bit more granular we get a little more precise, I should say, in our representation of probabilities if we take 1,000 samples. I think this might be better served by changing this to 50 and 500. Because what I really am getting at here is we have less trustworthy probabilities with less samples in a sampling approach, and I think that's an important thing to consider. So I'll change these back to 116 bits, and I just want to take a little bit of time to show a way that we can improve our sampling approach. So this code will all be relevant. We're going to use it, so I'll go ahead and put it in the Slack, and we'll go from there. Okay. All right. Sorry, my cat's meowing at me. All right, so when we're thinking about this, well, let's think about this from the point of view of performing many trials of these samples. So what do I mean by a trial versus a sample? These definitions that I'm using are a little bit arbitrary, just honestly. A sample is how many times we are sampling from the binomial distribution, right? How many times we're pulling a list of binary and counting up the ones. So we do that 1,000 times. How many times do we do that 1,000 times? Well, in both of these cases, we're only doing that trial of 1,000 samples one time. So a trial is sort of a container of a number of samples. And so if we want to improve, if we want to move our sampling distribution, our sample representation, toward what I'm calling the theoretical distribution, or what we'll see from either a closed formula or from if we have the PMF or if we have a counting approach, if we want to move in that direction with our counts or our probabilities, then we can take more trials of samples. So let me demonstrate that we'll do 500 trials of 1,000 samples. Okay, so this is going to look a lot like these prior functions, but we're going to have a nested for loop, essentially. So I'll call this binary sampling, and I'll say CLT. CLT in this case is a reference to the central limit theorem, which we aren't going to get into in this course. But essentially, because we're sampling more, we're going to smooth out we're going to smooth out and do a better job of finding the mean of each of the individual probabilities that's tied to a value of k. And a process that informs that might be the central limit theorem. So I'm just referencing the central limit theorem. It's a good thing to read about, but we won't get deeply into that at all in this course, although it does come up quite a lot when you are in the DSI. So we'll do a number of samples and say 1,000, and then we're going to do sample trials, which for every sample trial, if there's one sample trial, then we do 1,000 samples. If there's two sample trials, we do 2,000 samples, right? And so on. So let's do 500 sample trials of 1,000 samples. How many samples does that end up being? Well, it's 500 times 1,000, right? So 500,000. All right. So from there, I'm going to make a sort of like overall collection of results, and I'm calling that D out. And I'm going to say for whatever in range, the number of sample trials. So this is our outer loop. And for every loop in the outer loop, I'm going to build a binary sampling dictionary. I'm going to pass in the number of bits and the number of samples. Okay? So that gets us a single dictionary. And then we're going to traverse that dictionary for a key value in that dictionary. So again, we're going to do this 500 times by default. If the key is not already in D out, then we can say D out sub k, and I'm going to make a list here. Okay. I'm going to collect all the values in D into D out. And at this point, I can just append the value. So what am I appending here? These are the counts of occurrences, right? So for the key, or the value of k, I should say, for the value of k and the count, right? And, there's nothing wrong with calling this, calling this count, right? There's nothing wrong with doing that. For every time we encounter one of those, we pack it into this D out. So we're going to end up with a set of keys that represent the different values of k. The keys are going to be associated with a list of counts of those keys occurring across all those samples. And those lists are going to be different lengths, right? They're all going to be different lengths. I'm sorry. No, they're all going to be the same length, but they're all going to have different counts. Oh, wait, is that true? No, they are going to be different lengths. I'm sorry. I keep going back and forth on this, but in my head. But if you think about it, the least occurring items are, some of those won't even show up in the dictionary, right? There's a fairly low likelihood that 0 shows up. 0 observations will show up in this approach. And so what we might see here is we might get a 0. We might get, a 16. We might get those if we run many trials of these samples. So when this comes down to it, I don't want that list at the end of the day. I want the averages. So I'm going to say for key value in dout.items, I'm actually going to reprocess these, and I'm going to say d sub out sub k is going to be the average. It's going to be just the mean of each of those lists. And it might occur to you, well, some of these lists are going to be shorter than others, and so we're going to have more variability potentially in the more extreme values. We're not going to be able to trust the probabilities if we generate probabilities or the counts as much for, say, 0 or 16 if we're using 16 trials. Not sample trials, but 16 Bernoulli trials or 16 bits. Okay, so let's run this. Let's see how it does. I think one of the things that I think is interesting to do once we look at the PMF, we can compare the PMF to the results of this trials of samples approach. Number of sample trials, and that'll be 500. Okay, so we get D, we get this dictionary, and the first thing we can do is we can observe the counts, right? So observe the counts, and this will be for the key and the value. Remember we have to sort this in order to see it in order. It won't be in order automatically. It'll be in the order that it's added, and we can just observe the keys and the values, and then I think it's helpful here to observe the probabilities as well. So let's observe the probabilities. And with this, all we do is we take this value and we divide it by the sum of d dot values. And it's probably a good idea to round this. I'll just say round to let's round this to 5 places. Okay. So I think that looks good. And this is going to take a little bit to run, right? Remember, we're doing 500 of 1,000 samples. So I don't think this should be. I don't think it should be surprising. This takes takes so long. We are going to have somewhat more surety here, and part of how we can see that is look how much more symmetrical these are, right? These are very close to each other. 17,403 versus 17,355. 0 and 16. We're getting those in 16 trials. So I think we're probably getting pretty close. We're moving in the direction of, at least, the probabilities from the theoretical distribution. And when we look at these counts dictionaries, I'm not rounding these, right? I'm not flooring them. I'm leaving them as they are. These are the average counts that we see. Although, of course, once we get out here, way far to the right in this number, those stop being as meaningful, but that's fine. So, yeah, I think this is a good indicator of moving in the direction of what the PMF is going to tell us explicitly. So, why are we doing this? Why, right? Why would we go through all this trouble? The short answer is there is a concept in here that is fairly easy to sum up. One of the ways I would sum it up is more samples are better. That's a little bit simplistic, a little bit short, but in general, we can move in the direction of a closed form or theoretical distribution if we run more trials of a sampling process. We gain more surety. And I think you could claim the same thing as, if you're looking at a population of people and you're polling people, you're going to get a better idea of the sentiment of people, of people's opinions, say, on their interests, like maybe sets of interests. You can get a better sense of a population's set of interests if you poll more people. Now, the question there might start being, are you polling the same people twice, right? or does that matter? Is that, is that okay to do if you're considering the frequency of people's interests? Maybe that's fine. Maybe that's a good thing to do. If you're considering all of the interests in some kind of like absolute sense, the percentage of people who have a certain interest, then, the best thing you could do is probably engage everybody in the population, everybody, and that is going to give you a parameter to that population, right? It's going to give you a clear probability, in the sense of if you go and you find somebody and you ask them, what's the probability that they have this interest? Well, you can look at the parameter of that population. Generally, we don't have that option. And so this sort of resampling approach can be very helpful. The more you perform this, the more surety or the less uncertainty that you have in the prediction of, probability of, let's say, people having a certain interest. So, I'm an advocate in some way for this kind of approach. And I think, you can extrapolate this to a lot of other scenarios, a lot of other situations. Okay, so one limitation of what we've done here is that we have a fixed value of p, right? We have a fixed value of the probability of success on any given trial. However, we can go back to our original Bernoulli function, and we can rethink this approach just a little bit in order to be able to vary our probability. So I'm going to take this. I'm just going to snag this Bernoulli trial, and I'll put it here. And let's say I think I can leave this as is, although we do need to import random, which I'll do right above here so that I don't forget to paste this in. So from random, import random. So we've got this Bernoulli function, and it's going to return a 1 upon success, a 0 upon failure. So we can write a function that utilizes this called generate n successes, or generate n trials, generate n, how about generate n? I don't know. Because I'm using the word trial in so many other places, I'll avoid using it right here. But they are Bernoulli trials, right? So n trials might be a good name, but that's okay. Let's just leave it as generate n. So by default, we're going to generate 8, we're going to perform 8 Bernoulli trials. And this is easy enough. You can just make a list for whatever in range n, and then we can just say list.append will append a Bernoulli trial with probability p, and we can just return that list. So if we think about this, let's just print a version of this that where we have probability of 0.1 in 8 trials. So I think it's, it's fairly likely that we're not going to get a 1 in these 8 trials because 1 out of 10 is roughly what we would expect to see. And we got 1 1. That one we got 1 1. That one we got a 1. We got 3 1s. We got no 1s, right? And so this is a reflection of tuning this, tuning this a little bit so that we can accommodate a variable p. So let's rethink these functions from above. So we've got this binary sampling dictionary function. I'm going to copy this, and I want to show you kind of how easy it is to just adapt this to utilize Bernoulli. So we create a dictionary. I'll just change the name to, we're going to be able to vary the probability here, which means that we can add another parameter, 0.5. So we've got a dictionary we instantiate. We perform this a number of samples, and we're going to generate n. That's the name of our function here. pass in the number of bits, generate n, but we also need to put in the probability. So we've got our observed k, which is the sum of the binary that we're seeing. If observed k is not in the dictionary, we initialize it, we return the dictionary. So that looks like it should work. And the this accompanying code to run it, all of this should work as well. Okay. Although we'll need to just change the names really quick. So this is binary sampling dict with a variable p. So let me just do this a little bit more systematically. There we go. And we want to put in a probability, and maybe that probability can just be let's use 0.3. So probability of 0.3. And I think that's good. 16. Number of samples 100. Number of samples 1,000. I'm going to change this to 8 bits. And let's take a look at what this does. Okay. Oh, I should have put space in between these two. Oops. Okay, so let's see how that looks. Again, we get fewer values of k when we take 100 samples than when we take 1,000 samples. And notice that at this point, 2 is going to be our most, at least if we're considering this to be delivering us a probability, 2 is the most probable outcome. And yeah, why is that? Well, let's think about that. It turns out that, remember how I said, if you recall this, our expectation of a binomial distribution that has, I'll say a binomial distribution that has n of 8 and a probability of 0.5, that's going to be 8 times 0.5. So our mean, or our expectation, is going to be 4. It's going to be 0.5 times 8. So in this case, we're looking at something slightly different than that. We're looking at a probability of 0.3, right? And so this is going to be a different value. Our expectation is going to be 0.3 times 8. And so what is that? That's going to be 2.4, right? So our expectation, or our mean, is going to be 2.4. Although I'm putting mu here, what might be more appropriate, well, this isn't more appropriate, but this is the theoretical mean. What we are seeing as the most common output is 2. Does that mean 2 is the mean or our expectation? No, it is the modal output, though. It is the mode of of calling out and sampling from this. So something to look at, something to notice, is that 3 is more probable than 1, which makes sense because our expectation is 2.4. So notice our expectation can be between the actual values of k. And hopefully that makes sense in the way I'm describing it. It's if you have a discrete distribution, you can have an average or a mean or an expectation or a standard deviation that is not a discrete number. And that makes a lot of sense because that's sort of like a moment or a specific parameter of that distribution. Okay, so we can take this a little bit further, and we'll just take it a little bit further here, and adapt the that same trials of samples approach. So let me throw this in the Slack before moving forward. Okay. What did binary sampling CLT help us solve? From a high level, it helps us move in the direction of, it helps us get values that look more like the theoretical values of the distribution, the values that we'll see when we use the PMF. And binary sampling dictionary with the variable p. In the prior functions, we weren't able to vary the value, we weren't able to vary the probability of success of any given Bernoulli trial. The reason being, we were selecting zeros and ones with 50% probability. So all that really happened here is changing the underlying mechanism by which we get zeros and ones. So instead of choosing from 0 or 1, we're getting a 0 or 1 from Bernoulli, where we set a probability. So we can set that to 0.3 now for any given trial, which is much more like what we'll see when we use the PMF in a closed form approach. So let's sort of adapt this this CLT function here, the one that uses just binary that's generated with equal probability, and let's make this so that we can vary the probability. So this will just take a little bit of working. We just want to throw in, well, let's put in by default a probability of 0.5, number of samples, number of sample trials, that's all fine. Number of sample trials, binary sampling dictionary, although we want to change this to binary sampling with a variable probability, pass in the number of bits, pass in the probability, and then everything else. Oh, is that the name of that function? Oh, binary sampling dictionary with a varying probability. Let me just fix that. Okay. And then everything else should be just about the same. Just have to change this name in these. Oops. I think I need to uncomment this. Okay. Huh. Not sure why that's happening. That's really strange. Oh, because I'm only supposed to be calling it twice. Binary sampling dictionary, variable p. Binary sampling CLT. I'll just do that. Ah, because it only exists once. I'm sorry. Okay. Let's set this probability to 0.3. And we'll change the number of bits to 8. And we're going to take 500 trials of 1,000 samples. And so we should see the counts and the probabilities of this. It's going to take a bit, right? Took a little bit longer. Now, what we are seeing here is a distribution that has a different shape, right? It's still binomial, but I want you to notice that the shape of this now, if we were to draw this, is going to be something like that, right? Where, this is 2, this is 3, this is 1, right, 0, and so on. And we are getting up to 8, but 8 is a very unlikely event, right? K of 8 is a very unlikely event. Okay, so we've taken these views of binomial from a counting approach, right? Counting, and then from sampling. And I've kind of left the easiest for last, and that's, using the PMF, right? So this is going to be a breeze at this point. The coding on it is much easier to understand, and it's also much more likely that you're going to use the PMF approach. The reason why we're taking this sort of long trip into using the PMF is that it's really important to understand what's happening under the hood. And why is that important, right? The argument that I'm going to make for that importance is that you are learning how to think algorithmically. And when you're given a formula, let's say in this case the PMF for binomial, which I will put up here right now. When you're given this formula, all you have to do is plug in numbers, and that's going to get you to an answer, right? But if you want to think about how the process works that leads to this, that's more exploratory. If you want to dig into the phenomenon itself, that is more exploratory. It's a little bit harder to come up with that. And so if you want to understand the phenomenon, it's really good to code it. For the technical interview, you don't need to code that phenomenon necessarily, but you will need to code parts of it. Very likely need to code parts of it, right? Like, can you code the generation of a random list of binary? Can you process the bits in that binary in some way? Can you pack things into a dictionary? All of these come back to the same types of problems that are in the technical interview. And when you're in the DSI, you're going to be writing some of these algorithms from scratch. You're going to be seeing a machine learning algorithm and coding it from scratch. And so you want to get into the mode of thinking, how does this work? Or how do I design this, outside of the mathematical formulation? So this is the probability mass function for the binomial distribution. And you don't have to memorize it. We're not going to ask you to memorize it at any point, really. Even when you're in the DSI, if you can look it up, that is fine. But if you look it up, it's important to understand what's happening here, okay? So there are parameters to this. Actually, let me look at the questions before I go too far. Counting, sampling, under the okay. Generating a random list of binary is exactly that. It's simulating a bunch of Bernoulli trials. And that's important. That's an important thing to know that you can do. And you can take that to other phenomena, right? So, like, what is the name of the distribution that instead of having a binary outcome has one of 5 outcomes of equal probability? Or not of equal probability, of different probabilities. What's the name of that distribution? I don't know. I don't know that has a name, but it's a distribution that you can design if you can design a binomial distribution, right? And so if you're trying to model some phenomenon in nature that seems to do that, then being able to write that in an explicit way can lead you toward answers. It's a lot harder to arrive at answers that use a closed form. That it's a lot harder to figure out what the equation is. I mean, look at this equation. How hard do you think it was to come up with this upon observation of, like, coin flipping? You know what I mean? I think that's pretty amazing. I think it's pretty amazing that we have this formula. But there's a whole lot of procedure that went into the development of that formula, right? So, more often you're going to be developing a procedure that gets you to an understanding. The mathematical formulas, there's mathematicians out there who are probably going to handle that later on. It's probably not going to be you. No offense to any of you. Maybe it will be you, but I know that what I find out in the world is like there are these moments where I discover, oh my gosh, this phenomenon that I think is much more complex. Actually, I can root it into a simple mathematical formula, and that's really cool. But that was also really hard to discover. More often than not, it's some like simple linear function that, the underlying process, we can just put in a bunch of inputs and get an output, and you don't need a neural net to do that, right? You can just use a linear regression, which ends up telling you, okay, this is a linear function at the end of the day, and here are your coefficients. But something like this is nice, but this is for binary, or for a binary output. What if you have output of 5? 5 different possibilities with varying probabilities of each. That's a much different level of complexity, but we can still solve it procedurally, which is a gift. Like, we can do that. We've got these great languages that allow us to do that kind of thing. So let's think about this PMF much more directly, right? So as we talked about with the binomial distribution, we've got 3 parameters. We've got n, we've got p, and we've got k, where n is the number of trials, right? P is the probability of any given trial, and k is the number of successes for which we're looking for the probability. We can kind of break this down a little bit further if we're looking at this function. Let's think about, oops, I didn't mean to actually draw on that. What's this, right? Turns out that this is n choose k. This is just a different way of writing it. That's n choose k. Combinations is right in there. Why is that? Because we're considering how many combinations lead to, say, 5 successes in 10 trials or something like that. We've got the probability, we've got the complement of the probability, we've got the value of k, and we've got, I don't want to say the complement of the value of k, but we've got kind of the, the number of trials minus the value of k. So there's a pattern here that actually turns up in a lot of other functions, especially this p times 1 minus p, that comes up a lot. This, specific chunk right here. So this turns out it's not hard to code this this little function up, and we're going to do that shortly. Let's think about what we need in order to do that. So obviously we need combinations, right? What do we need for combinations? We need factorial. So the first couple functions I'm going to have you write, I'm just going to have you write factorial and combinations really quick. And I think that will kind of get us off the ground. And then coding the actual PMF shouldn't be too difficult. So let's take 5 minutes and code the functions that the PMF will depend on. And I'll just set our timer to 5. And yeah, go ahead, code factorial and code combinations, and there's the combinations formula for reference. Awesome. So a lot of you coded good solutions to this, and I'll just write this really quickly after I comment out this code. Okay, good. So we'll write factorial, and then we'll write combinations. And factorial is going to be n, right? And then we're going to say there's a product. I'll set it to 1. I'll make this a little bit bigger. Okay. Let's try that again. Okay, so product is 1. For num in range, we'll go to 1 to n plus 1, right? And the product is going to be multiplied by each of those numbers. I could just set this to 2, which I would usually do, and then we can return the product. Okay, so combinations is n choose k, and we can say this is just the factorial of n divided by the factorial of n minus k, and that is going to be multiplied by the factorial of k. I want to make sure to put that in parentheses, and then all of this I'm going to cast to an integer because, well, it doesn't make sense for it to be decimal valued. Okay, it wouldn't hurt anything if it is, but it doesn't really make sense for it to be. So we're going to use these in writing the next function, which is going to be coding the PMF. So so combinations is here, right? We can see combinations explicitly in the PMF, but I want you to think about why that is, right? And I think if you take this back to how we've been counting and looking at all the different ways that that we can get a certain number of successes when we count in binary, I think that gives some good intuition as to why we think of combinations as being a prime component or an important component of the binomial PMF. Okay, so with that said, I'm going to have you code the binomial PMF. So let me just pull this slide up. Let's do 4 minutes on this. So notice there are 3 parameters, n, p, and k, and here's your formula. Of course, this is going to depend on the prior combinations formula. So let me set a timer for 4 minutes and go ahead and get started. All right. Okay, so let's just code through this. This is going to be a pretty direct translation of the formula that we're seeing, and I'll just kind of do this kind of a couple steps at a time. The only real danger in this when you're coding this is that you mess something up a little bit. Like, it's very easy to make typos when you have formulas. So this is going to be combinations, right? That's the first part. It's going to be n choose k. And then the next part is p to the k, right? P to the k. And then the next part is going to be 1 minus p, that is, to the n minus k. When I'm writing these formulas, I'll usually space them out like that, so they're really easy for me to see. And that should be it. So we can use this to answer certain types of questions. And yeah, let's think about a question here. This is a question that we could have answered before, given our prior approaches, such as what is the probability of getting 7 heads in 12 coin flips. So we can define n, k, and p, where n is going to be 12, k is going to be 7, and even though we don't explicitly have the probability here, it's a fair coin. And so we're going to assume a probability of 0.5. So if we just call this like so, we should get a probability. 7 successes in 12 trials. What does that look like? That is 0.193. Now, if you recall, oh, we didn't do 12 trials. We did 8 trials, didn't we? Okay, never mind. That's something, if we have time, we'll revisit. But this is an answerable question at this point. So let me go ahead and paste these in. And we'll kind of, and we'll keep building from this idea a little bit. Okay. So we can answer questions now. And I think that's a really important thing to consider. That this is a fairly, like, if we have these formulas, we can answer these questions. We can look at a phenomenon from the point of view of, like, well, how do I answer this? And I think that the power of that is very important. It's, I think it's also, very important to understand how to, well, let's say, how to build a binomial process or some other process. I think that is also important. But usually the first thing people will see is these formulas and how to use them. So that said, let's do a couple more of these, and I'll have you do these. So that will be 1, and we'll just take 2 minutes on that. So go ahead and solve that. Sitting on a park bench, you observe geese walking by. There's a probability of 0.3 that any goose walking by has black feet. What is the probability that 4 out of the next 12 geese walking by has black feet? So go ahead and solve that. Okay, so let's think about this. This sitting on a park bench. You observe geese walking by. Really, the key to these is going to be defining. Well, the first thing is discerning whether it's a binomial problem. That's the first thing to consider. But then defining n, k, and p. So we've got n, k, and p. And what are these? Well, n is 12, right? We're thinking out of 12 geese, we're curious about the probability that 4 of them are going to have black feet. And the probability of any one goose having black feet is 0.3, so we can just plug these numbers into the binomial Pmf. So let's see what that is. 0.231. And again, it's really about discernment of the problem. And we're going to think about that quite a bit more when we start looking at Poisson specifically and geometric. We're going to have to start discerning if something's a Poisson problem from a geometric problem from a binomial problem. And there are good ways to practice that. One of the suggestions, if you watch Study Hall today, is that I have, one of the strong suggestions I have is write some of your own problems. That will help you quite a bit. Okay, so we are at the middle. Let's take a 6-minute break. And yeah, I'll see y'all back here in 6 minutes, and we'll continue toward the CDF and some other concepts related to binomial. All right, so kind of picking up and continuing here. Let's talk about the CDF, and we're going to spend a little more time on the CDF here than we did prior. We're going to have a specific CDF function mathematically represented, and I think it's important to kind of break this down. So here we have the formulation, a reformulation of the PMF into something that's kind of an iterative process. And I think anytime you see this summation symbol, this sort of giant E shape, it looks a lot like a sigma. Anytime you see this, sometimes it's called capital sigma, but I think some people will argue for the differentiation between summation and sigma, but I don't care. Sorry, it's a bit of a tangent. So the this symbol for summation, this implies a for loop, right? This implies that we are going to start at 0 and go up to k, and for every value, right, up to k, we're going to get the PMF. So this will be the PMF of 0, the PMF of 1, and 2, and so on, up to k. And we are going to add all of these together. So what does that look like in terms of Python? It's not much of a stretch from what we're seeing right here. So we've got the binomial CDF, the binomial PMF. We can just utilize this function to code up the binomial CDF. So I'm going to do that really quick, and just to demonstrate it. This is just going to be a for loop and an accumulator when we get down to it. So this will be the binomial CDF, and we're going to pass in n, k, and p. Let's just do n, k, and p. And we'll say this is a cumulative function. We're going to get back the accumulation. I'll just call it cumulative. And I'll say for k in range, let me name this k high. For k in range k high, that's the highest value of k that we'll consider. And I will change that to a probability of 0.5. We can go from 0 up until k high. We want to include k high. The CDF will include the upper bound. Okay, and so I'll just say cumulative is going to get the binomial PMF and kp, and we can return cumulative like so. Now we are not gathering all of the individual probabilities, we are summing them. And so we can use this to answer, I'll just use it to answer a quick question as a template, and then I'll give you all a couple questions. And let's say the probability that I don't know. I'm always going back to puppies and kittens and stuff. The probability of the puppy at the pound, is it even called the pound anymore? I'm not going to worry about it. The probability that the puppy at the pound is cute is 67%. Let's say that, or 0.67. What is the probability that the next 20 puppies, no, not the next 20. How about that less than 11 of, what's a good way to think about this? That 11 or less puppies you observe at the pound will be cute. 11 or less puppies out of the next 20, out of the next 20 you observe at the pound will be cute. Okay, so How do we solve this? Well, we define n, k, and p. So n here is going to be 20, because we're going to observe 20 of them. K high is going to be what? It's going to be 11. So we're going to look at everything from 0 to 11 of them. And then the probability is going to be 0.67. So that's a directly answerable question like that. And the result of that is there's a 0.18 probability that, or sorry, a point, did I say PMF here? No, I said CDF. Okay. There's a 0.182 probability that 11 or less of the next 20 puppies you observe at the pound will be cute. Okay. So I'll paste this in, and I'll give you all a couple questions to do. Of course, this is dependent on the prior functions. So there it is. Okay. Yeah, I think shelter is probably a better word. But, you know, I put pound in there, so let's just go with it. Okay. So this isn't as cute of a problem, but well, we'll see. We'll see how this goes. Okay. There are 8 components in parallel and functioning independent of each other. At least 3 of those components need to be operational for a given circuit to function. The probability of any given component being operational upon observation is 0.7. What is the probability that at least 3 components are operational upon observation? Okay, so there might be a little bit that I should explain here. We're talking about components in a circuit, and maybe it's helpful to have a visual on this. Let's say we've got 8 components, and they're all what we think of as being in parallel, right? So if one of these components goes out, it doesn't mean that the others go out. They can all kind of operate independently of each other. So we need at least 3 of these to be functioning. So, you know, that would still be a functioning circuit, even if 5 of the components were out. And maybe they go out intermittently if we want to make a better explanation of the problem. This is sort of a classic binomial type of problem, just to be clear. So just think about how to use the CDF in this and go ahead and solve that. I'm going to put 2 minutes on the clock. So go for it. Okay, so let's look at this. Find my editor, and I'll just paste the problem in. Okay. This kind of problem often gets people tripped up, right? Because we're not asking for the probability of 0 components or 1 component or 2 components working. We're asking the probability of 3, 4, 5, 6, 7, 8, 9, or 8, up to 8, right? So we're asking for the complement of the probability of 2 or less working. So how do we think about that? It's really just, so we can take the binomial CDF, like so. There's an n of 8. We can figure out the probability of 0, 1, or 2. And there's a probability of 0.7 that a given component is functioning upon observation. And we can subtract this from 1. And that should work for us. So print 1 minus the CDF. Oop, not timing, but... And it looks like there is a very high probability, right? 0.98, really like close to 0.99 probability that at least 3 of these components are operational upon any given observation. And I think that's maybe a little bit telling of a good way to think about parallelism in components, right? The more redundancy you have, the more likely that operation, that circuit, that component is going to be functioning. So cool. I think a few of you got to the correct answer on that, which is great. Okay, so I'll go ahead and paste that in. And we're getting very close to wrapping up binomial. We've covered it in, from a number of different angles, really. And I think we won't spend quite as much time on the other 2 distributions, but there is something we're going to do, I want to say sort of over and over again. And because of that, because of this style of problem, I'm going to have you do a quick code up of the Binomial Pmf dictionary. Now, this should return a dictionary where the keys are the values of k, and the values are the probabilities of k events occurring. Okay, so realize that this is in relation to the PMF, not the CDF. We can also look at the CDF dictionary, which is a very easy function to extrapolate from the PMF dictionary. So go ahead and work on this. I'll put 5 minutes on the timer. Yeah, so code up the Binomial Pmf dictionary. Here, I'm going to put a couple more minutes on this and after I explain it a little bit more. What is the Binomial Pmf dictionary function doing exactly? We're going to, maybe I can represent this really quick. You instantiate a dictionary, right? And then you call out, you're going to loop from 0 up until k high, right? Or sorry, I said 0. I meant to say k low. So you go from k low up until k high, right? And this is going to be each value of k. So this is going to be, I don't know, k1, k2, k3, k4. These are all going to be keys in your dictionary, right? D sub k, I'll just say kn. Now, for each key, you're going to have associated with it the PMF of that value of k. So if you start this at 0, this is going to be the PMF of 0. This will be the PMF of 1, PMF of 2, and so on. So this is the PMF of k1 in this sense. So what you get out of that is a dictionary where you have, for example, 0 and the probability of 0 successes, right? So 0.01 something maybe. 1 is going to be, I don't know, 0.03, and so on. So you get a dictionary where the keys are values of k and the values are the probabilities of k successes. So let me put 3 more minutes on the timer, and we'll go from there. Okay, so I'll put timer 3, and for those of you who have that clarified understanding now, go ahead and finish solving this. All right, let us solve this this function. Okay, so I will just call this binomial. Sorry, let me reference back to the prompt really fast. Binomial CDF dictionary. Binomial Pmf dictionary, that is. Okay, so binomial Pmf dictionary, and we're looking at n trials. We're going from k low to k high with a probability of 0.5 by default. And we instantiate a dictionary. That's the first step. And then we just go ahead and say for k in range, we're going to go from k low. Sorry, let me keep that there. K low to k high. Plus 1, we want to be inclusive. And d sub k is going to be just the binomial Pmf and k and p. And then we can return the dictionary. So we can traverse this pretty easily. So I'll go ahead and do that. Let's set this n as 8, k low as 0, k high as 8, and the probability at 0.25. And then we can just say for k, v in d.items, and we can print the result of that. So the key and the value for these. Okay. So here we're able to look at the probabilities, the sort of true probabilities for this distribution. Now, what's a quarter of 0.25, right? We're seeing that pretty clearly. So again, this is going to be it's going to kind of be bulbous around 2. 2 is closer to our expectation, or is our expectation, and we have a tail out to the right. So let me go ahead and paste this in. And I just want to reiterate that this is a type of function that you could be very well expected to write a PMF function, a PMF dictionary function, or a CDF dictionary function. So I'm going to just show you how you can change this for the CDF really fast. So if I want to change this for the CDF, I'll change that to CDF, and I will change this to CDF. I think that'll work. And just want to point out what this dictionary looks like. Oh, that's not quite right, is it? What is going on there? Binomial Pmf. I see. There it is. I didn't change the name of the function call. Okay, so just to kind of drive home an idea around the CDF, I want you to notice how these probabilities grow. We're accumulating, and so naturally, when we get up to 8, what is the probability that we have a success within 8 or fewer trials? Well, it's 1. We're either going to have 0 successes, 1 success, 2 success, 3 successes, 4 successes, up to 8 successes. So I'll paste in that CDF code really quick. Oh, the output for the Binomial Pmf dictionary. Sure. And I'll paste in the CDF code. All right. So that's all we're going to cover with binomial. We covered a counting approach, a sampling approach, and then the closed formula approach. The next two distributions that we're going to think about are Poisson and Geometric, and we're going to spend. We're at least going to cover Poisson. Oh, sure. I'll paste the output for the CDF as well. We might not. We might skip over Geometric. At this point, at least for the next few weeks, we don't have a specific interview that concerns itself directly with geometric. We do have a geometric process in one of our interviews, but you don't necessarily need to understand that. I think covering 2 of these distributions is probably going to be sufficient for us, but if we do have time, we'll get into geometric, or at least touch on it enough to, to see it as another distribution built on a Bernoulli process. So let's think about Poisson. Poisson is one of my favorites. I think it's a really interesting distribution, and it touches on quite a lot of different phenomena and things that are interesting and difficult to describe at different times. So we'll talk about what some of those phenomena are. We'll talk about the Poisson Pmf, and we'll try to relate Pmf to binomial in a direct way. The diagram for D sub k. Oh. This diagram? Oh, sure. I can copy this and I'll paste in an image of it. Okay. All right. So let's talk about the Poisson distribution. So Poisson is going to it's going to feel different from binomial. But I do want to relate it back to binomial because I think there is an interesting relationship there. Poisson, it's spelled like poison with 2 S's. You can think about this as meaning fish, right? Poisson, I believe, is fish in French. And one of the ways that you can think about this is you have a bunch of barrels on a dock, right? A bunch of barrels on a dock. And, say there's a ton of barrels here. And on average, you expect there to be 10 fish in each barrel. So there's an average of 10 fish per barrel. What is the probability if you pick a barrel that there will be 7 fish in there? Okay. So that's the kind of question you can try to answer with Poisson. And that may not be the best example of Poisson, but it is kind of a nice mnemonic, right? So what we think of as the average, I think it's nicer to think about this in terms of time, to be honest. So we'll revisit some other kind of physical world problems, but let's think about this in terms of time. So we've got a timeline here, and we have an average number of events that we expect to see. We're going to call that lambda, okay? So lambda is the average number of events in a certain span of time. So we want to be careful about that span of time concept. Let's say this is in between 0 and 10 minutes. And let's say these are, people walking into a small store. Within 0 and 10 minutes, and let's say we have a lambda of 5 people walking in and out of this store in 10 minutes, where do these people, at what moments do these people walk in? That's the real question. And so, if we're thinking about this on average, maybe they all walk in like that. So maybe they all walk in like that. Maybe there's 5 of them. Maybe they walk in all kind of in the last couple minutes. There are a lot of different ways for that to happen. In fact, there are infinitely many ways for that to happen. But we do have to put some constraints on this. This expectation, this rate, this average rate is assumed to be consistent. Okay? We assume that to be consistent. Also, we assume, if these are all people, we assume that they're not traveling together. We assume they are independent from each other. And they are also discrete. A person is just a person. It's not 1.3 people or anything like that. They are identically distributed in this time frame. So they could happen in any moments, except just to be technical here, they cannot happen in the exact same moment. They can't go enter the store in the exact same moment. Although if you think about time is continuous. If we're ultimately precise, if we are absolutely precise and we have infinite precision, that's not even possible, but it is one of the constraints that is mentioned for Poisson. So we can answer certain kinds of questions with Poisson, with the Poisson Pmf. If we know that there are 5 people on average who are going to come into the store, we can ask the question, within 10 minutes, we can ask another question. We can ask the question, what is the probability that 8 people come into the store in 10 minutes? We can ask the question, what is the probability that 5 people enter the store in 7 minutes? We can answer these kinds of questions because we have certain assumptions about the Poisson process. This span of time, and this is interesting, if we're considering a lambda of this lambda of 5 people going in the store in 10 minutes, well, what is our lambda for 5 minutes? Right? What is our lambda for 5 minutes if we expect 5 people in 10 minutes? What is that lambda? Exactly, it's 2.5. So that would change to a lambda of 2.5. And can you have on average 2.5 people? Yeah, you can, because it's an average, and you're not going to have exactly 2.5 people because that won't be possible. But you might have 3 people, and you might have 2 people with kind of equal probability. So thinking about Poisson and the kinds of questions that we can answer with the Poisson Pmf, well, we are going to have certain things in the PMF. We're going to have lambda. This is the average frequency. It has to be related to something. It's related to time, or area, or volume. There are times where we can think about this in relation to pages in a book. Like on average, there are 200 words in the page of a given book. What is the probability that there's 180 words in some randomly selected page of the book? That is a type of question that is Poisson-like. Poisson may not be the best way to answer that, honestly, but it is the type of question that you might find in a textbook that you can approach with Poisson. So lambda is the average frequency related to a given amount of time. Lambda can be adapted to different intervals of time, area, or volume. And the way that this function looks, the probability, given lambda, and you're asking about k events happening, the probability is going to be e to the negative lambda, where e is Euler's number, multiplied by lambda to the k over k factorial. So again, we need factorial here. I'll just go ahead and copy-paste factorial from over here somewhere. Let's just find it. No need to rewrite it right now. Just throw that in there. We're also going to need e. So from math, import e. Now we could import e and factorial, right? Factorial exists in the math module, but let's just leave the actual function here. Okay, so let's think about a Poisson problem, a specific Poisson problem. So on average, look at this one. On average, 10 people visit the ATM in an hour. What is the probability that 12 people visit the ATM in an hour? Well, the way we answer that is we just fill in these values, right? So lambda here is our average. That's a lambda of 10. So lambda is 10. So this is going to be e to the negative 10 multiplied by 10 to the what? Well, k is 12. And so we can rewrite this as e to the negative 10 multiplied by 10 to the 12th over 12 factorial. Okay. If we were to work that out, that would be somewhere around 10, a probability of 10% roughly. There's a 10% chance that 12 people will visit the ATM in an hour if we expect 10 people. Keep in mind that we can adjust these. If we have a lambda of 10 people in 1 hour, well, how many people in 1.5 hours? That's going to be 15 people. How many people in 2 hours? That lambda will be 20 people. And so this is the kind of question that we can use the Poisson Pmf to answer. Okay. So I'm going to have you code the Poisson Pmf function. Let me go ahead and put that up here. And feel free to import e, and well, I'll go ahead and, well, you should have factorial somewhere handy, I think. So feel free to use that, or also import factorial from math. So let's take, let's take 4 minutes on this. It's a pretty direct coding of the function itself. Okay, go for it. All right, so let's just code this up really fast. So I've got factorial here, and I already imported e. We can go ahead and say Poisson Pmf lambda. I like using lam and k, and we can just return lam to the k multiplied by e to the negative lam divided by the factorial of k. So that should work, and now we can answer, maybe we can look at that earlier question. Where was it? It was, on average, 10 people visit the ATM in an hour. What is the probability that 12 people visit the ATM in an hour? Now that we have this function, we can answer this. We can say, just call Poisson Pmf and set lambda to 10 and k to 12. So let's see what that gets us. And we should be calling this on Poisson. And I should probably print it if I'm going to do that. So here we go. So it looks like somewhere around 0.095 probability that 12 people will visit the ATM within an hour. Okay. So now that we have the Poisson Pmf, we can kind of explore. I'll take a few minutes here and explore its relationship to binomial, and we'll wrap up there for today. And then I think tomorrow we'll cover Poisson for a bit, and we'll either go into conditional probability or continuous distributions. We're going to do, I think, one or the other. I'm not sure which yet. But this question, what is E? So E is Euler's constant, Euler's number. There's a playlist. Let me track down this playlist where I do some exploration of E, because I think it's one of those things that it's really interesting to dig into and kind of generate through a whole bunch of different means. So let me see if I can track that down really fast. It's one of those things that I sort of wish we could cover directly in class, but it is kind of this emergent number, and I think that I think it's interesting. So there's a playlist of 4 videos, and I'll just copy the first video in here. So you should be able to find the other 3 based on that one if you want to dig into Euler's number. Cool. So kind of to that effect, we are going to think about this a little theoretically, and so Poisson is related to binomial, and I want to kind of explain why. So the binomial distribution will tend toward Poisson under certain conditions. So binomial will tend toward Poisson. I'll just put it like this instead of writing that out. As n goes to infinity, okay, and the n in the binomial distribution goes to infinity, and effectively the probability heads towards 0. And lambda, which is equivalent to n times p, right? N times p is this is going to stay constant. So how can we kind of explain that? How can we explore that? So let's recall the binomial Pmf, and that's going to be, let's say, the probability that x is k. This is n choose k, multiplied by p to the k, multiplied by 1 minus p to the n minus k, right? And we can think of the mean, or the expectation, right? The expectation of x as being np, Okay, that's what we would expect, right? 10 coin flips of a fair coin is going to be, we're going to expect to see 5 heads. So the Poisson Pmf is, we can just represent it like this: probability of lambda and k. This is going to be e to the negative lambda multiplied by lambda to the k over k factorial. Okay. So the mean of a Poisson distribution is lambda, right? So our expectation here is lambda. If we set lambda equal to n times p, then we can rearrange this a little bit, and we can see the probability, p, is equal to lambda over n. Okay? So that's going to be helpful for us. And we can then, we can take this a little bit further. We can rewrite the binomial Pmf to be the probability that x is going to be k, k taken from Poisson, is n choose k, n choose k, multiplied by lambda over n, right? So that's our probability. Probability is going to be equal to lambda over n. That'll be raised to the k, multiplied by 1 minus lambda over n to the n minus k. And then what we can do is we can grow n toward infinity. And that is going to effectively drive this value here, right? If we think about this as being representative of p, as n goes to infinity, p is going to go towards 0. And this is going to approach the result of the Poisson Pmf. Now, how can we demonstrate that? Well, it turns out we can demonstrate that with Python pretty easily. So I'm going to just paste in combinations and the binomial Pmf, and we'll start there. So let me find my text editor. So we've got the Poisson Pmf, but let's put the binomial Pmf in here, which I will just have dependent on combinations. And so let's start with an n of 1, okay? And we'll fix lambda at 10. So we'll have a lambda of 10. I'll call this lam instead. And let's have a k of 10. So in the Poisson Pmf, if we have a lambda of 10 and a k of 10, that is going to end up being 0.125. So I'll type this really fast because we only have a couple moments. But we can take n from k up until, let's do just 10,000, and let's print the result of binomial, where we're going to just take the binomial Pmf, pass in n, k, and p, where p is going to be equal to lambda over n, right? And so n is going to grow, lambda is going to move towards 0. And we can also print the Poisson Pmf, and we'll just round the Poisson Pmf, lam, k, and we'll round that to 7 places. Oh, I think I actually want to round the other one to 7 places as well. I don't think I'm doing that. Okay. And let's watch this trend. Let's watch these trend toward each other in this last minute. And this is just, building this idea of the relationship between the two. So let's do Python Poisson.py and watch binomial is heading in the direction of Poisson pretty explicitly, right? We're getting down further and further toward 0.12511, which is a lambda of 10 and a k of 10. So this is just a way that we can build that relationship. There's another visual way that we could do that as well, in terms of, how we subdivide a segment of time. Do we divide it evenly? Because if we divide it evenly, we can think about a segment of time as being like a binomial process. For every 2 seconds, we're either going to have an event or not. But then if we divide that into 1 second, or then to a half second, and then to a quarter second, and so on, the more we divide that, the more we're approaching Poisson, which is really what we're seeing here. It's essentially the same idea, but here we're, the way that we're doing that is we are increasing n, which is the number of trials, which is increasing the even subdivisions for what we're thinking of as a span of time, or a measure of area, or anything like that. Yes, let me, I'm going to go ahead and let's call it here, and then I will, I'll paste those things into the Slack, and we'll be able to look at those directly. So thanks so much. I'm going to spin down the recording, and I'll stay on for questions for a bit.